nice to be here, and I'm here with my colleagues Richard Ortiz and Jonathan Teresa, and together we were working with postdoc advisor Jonathan Everling, PhD. Our project was designing and understanding mathematical models and control and feedback control. In other words, automation. So I would like to start off by showing you guys a small clip. Here we have a quadcopter, and notice what's going to happen. So the big question here is, will the glass fall? Well, let's find out. As you can see, the quadcopter is able to maintain the glass upright, and this is possible because of automation. Automation gives us the ability to leave a mechanical system by itself and rely on it to accomplish the task. So how does automation work? We start off with the plant. Which is our physical system. From there, we get an output, and we are able to measure this output to gather our measurements. We then compare this to our reference. Our reference is what we want the system to do. What is the command that we are given? What is the task? Then that later on goes on to the controller, and the controller is going to determine what needs to be done in order for this task to be accomplished. From there, we get our input, and that input is going to go back into the plant, which is our physical system. Let's take an air conditioned room, for example. That's going to be our plant. And from there, the output would be the temperature of the room. We are able to measure the temperature of the room using a thermometer. And those measurements, the temperature that's in the room currently is going to be compared to the reference, which is the temperature that we have set up on the thermostat. The controller in this case would be an AC system. So the AC system is going to either turn on or turn off in order to accomplish a task, which in this case is get the room to the temperature that we have set up on the thermostat. For our experiment, our plant was not a quadcopter. It was not an AC system, but a gantry crane. We applied Newton's laws of mechanics to our gantry crane, which in this case is our plant, and we were able to formulate a mathematical model specifically for our gantry crane. From there, using mathematics, we were able to design a controller algorithm, and before we were able to apply it to a real-life gantry crane, we had to run some simulations. If the results that we got from our simulations were the results that we were looking for, the results that we wanted, and we then later on applied it to our experiment.
So it's also imperative that we inform you that our research that we do with the gantry crane isn't groundbreaking research, right? However, the idea of automation is. It's being put into everything that we use once again. Autopilots, our laptops, our phones, pretty much everything uses automation. So the idea behind this was to get us comfortable with the idea of automation and how the process works. So we use the gantry crane for that purpose. The gantry crane, most of us has probably seen this before. If you ever pass by ports or anything, we use these. They're usually industrial size, and they carry crates or large cars, or whatever you can put your mind to it to get these things to move. But they're very large, and they carry very big loads. And how the gantry crane works is that up top there's a cart, and that cart has the ability to move. It moves across the X direction, in our case, and that allows it to move left to right. And that cart will have a load hanging from it down here at the bottom, and that's generally what we want to move, right? So as that load moves naturally by the physical principles of the system, it's going to cause the load to swing when we stop moving. If we give it a velocity, as soon as it stops, that load still has some momentum, so that's going to translate into an angular swing. So that's why we get this angle here. So that moves on to the idea of mathematical modeling. How do we mathematically model this gantry crane? Well, we have to take those things into consideration when we model this. So to the right, most of us have probably seen this. That's Newton's second principle mechanics. It says that the sum of the forces in our system is equal to the mass times the acceleration of the system. You hear that a lot, on TV and science movies and stuff. It's a very common equation, and it's a really fun one. And we were able to use that idea, except we use it in an equivalent form. This is the Lagrangian formalism of mechanics. And this form here allows us to actually take into consideration here we have the kinetic energy minus the potential energy. And we're actually using energy considerations to solve this problem in our system. So the output from that equation, we were able to derive this differential equation. And this differential equation down here is actually our mathematical model. Lots and lots of symbols, right? Okay.
So once we had our mathematical model, we had to consider some aspects. What do we want? What do we think is important in our system? What do we not think is so important in our system? We do these kinds of decisions in our everyday lives. These are called trade-offs. So say, all you ladies out here, including myself, probably have the same issue. We're looking for the perfect guy. It's really hard to find a guy that's rich, smart, and handsome. So we have to do some trade-offs. So say we're looking for a guy that's smart, has a good amount of money. He'll probably be somewhere right here. And notice how that's really far away from the handsome corner. So again, it's a trade-off.
My significant other does not have a problem with this one, right? Okay, so in considering our system, actually, the controller design of our gantry crane, the trade-offs that we had to face were speed and energy efficiency. Okay, so if we wanted our gantry crane to get the load to its destination as fast as possible, well, that's going to cost us energy, right? So that means we need lots and lots of energy for that to happen. However, if we wanted to be very energy efficient, which usually translates to cost efficiency, then that means we're probably not going to have the quickest time, right? So these are the types of things that we analyze in our gantry crane system. And we can see that here. This top graph is the movement of the load itself. This blue line here represents where we want our load to be. It's 0.5 meters. This y-axis is in meters, so 0.5 meters. We wanted our load to move 0.5 meters to the right. And it did so in the amount of time here, so the x-axis is our time. And as we could see from the green curve, if we achieve a very fast time, just about 1.5 seconds there, down here on the bottom graph, it shows us that that actually required much more voltage than the other two curves. So if we took the other end of the spectrum, the energy into consideration, that would be the blue guy here. So right here we have our blue curve, and it shows us the voltage needed to move when we're considering energy as our top priority. And it took a lot less voltage than the green curve. However, as you see up here on the location of it, it took much, much more time, just about 3 seconds instead of 1.5 to reach its destination, right? So the middle ground in this case would be to take this red curve here. And the red curve really considers both. It says I want to get there in a decent amount of time, but I also want to try and control how much energy I use. So that's the middle ground there. And we can see it just did it a little bit slower than the green curve, which is very considerable by saving that energy.
Okay, so here we have the actual gantry crane that we used. So it's our experimental setup. As we can see, we have the cart up here, which is resting on the rail, which will be the axis for our point of reference. And we also have the load down here, which as the system moves, the load will swing and create our angle. Yeah. This is one of our initial experiments. We will be playing a video, and the main thing that we have to focus on here is the distance the cart moves towards its reference point, and as the load swings. And as the video plays, we will notice that it overshoots the reference point, and it has to adjust for that. And we also notice that the load keeps swinging. So here we're going to be comparing the data from the experiment we just ran, shown in the red line, to the data of the simulation, shown in the green line. So down here. And basically, as we can notice, both data sets are fairly similar. This demonstrates that our mathematical model was a successful representation of our physical system. And we can also notice that after around 5 seconds, our data sets start showing a little difference between there. Here they're pretty much following each other. And then after, we see the simulation flatlines or stabilizes, while the physical system keeps oscillating. This is due to the fact that we did not include friction into our mathematical model. By not including friction into our mathematical model, the simulation, like I said before, stabilizes. Unfortunately, for our physical system, we cannot take out friction, and this stops our cart from moving and keeps the load oscillating, like you saw in the video. that's just a way to prove how the mathematical model does not have to be perfect, yet our designed controller is still going to function properly. Here we're going to have another example demonstrating the versatility of our controller design. While the video plays, okay, so here we're showing how the system can respond to unexpected distresses, here being Richard moving the load, and it will correct itself. And we can also notice how now, instead of just having locks in our system, we added some extra mass. So that's still not in play with our mathematical model, but the physical system is still working properly. Okay, and basically by showing the versatility of our model in resolving unexpected issues, and by showing how successfully demonstrating the physical model, we're able to say that we successfully designed a mathematical model and designed the controller for it.
Further concluding that, guys, so the idea of automation is that we're able to leave a mechanical system by itself and it does the task that it's designed to do. So by having that extra mass on the system, it wasn't interpreted into the mathematical model. We didn't consider that, but it still functioned properly, which further illustrates the fact that automation is very powerful. It can consider these other things that we don't necessarily take into account, and it reacts to them, and it could sometimes still control those things, thus finishing the idea that we were successful with this automation. And once again, we'd like to say thank you. It's really fun being here. I had a great time, and I'm sure my peers did as well. So we owe a big thank you to the Electrical and Computer Engineering Department because they allowed us to use their labs, even though I don't think my graduate, our postgraduate mentor, is actually part of their lab. So thanks to them, right? We want to thank Jonathan Epperling, our postgraduate mentor, PhD back there. He's been really great. We had tons of fun with him, and he's an amazing mind. We got to tap his brain on tons of different subjects with him too. So thank you, Jonathan. And then, of course, we'd like to thank our super mentor, Dean, Wendy for having us, and Jens. Thanks to you guys, we're actually here, and because you guys outreach to our school, and that's a big deal for us, because this is an opportunity, so thank you guys.